Welcome to Khetz Tutorials, and in this video I'll be talking about the theorem of Pythagoras. So in previous grades you basically just dealt with it without really looking at the proof of it or what actually happens or what it actually means. So in this video I am actually going to show you the proof of this theorem. But before I do that, we also have to prove something quickly. So I'm going to draw a right-angled triangle. And I'm going to make two more triangles inside this by drawing a line from there to there. Right? If I can just finish this line, maybe. Okay, let's do this. So if I draw a line from there to there, then draw another line from there to that point, right? That's much better. And so this is a right angled triangle. I also have right angles over there, which is basically 90 degrees. So here I have D, call it 1, call it 2. Here I have A, A1, A2, and here I have C, there I have B. All right, so the first thing which we want to prove is the following. The statement says a perpendicular line from the vertex of a right-angled triangle to the hypotenuse, which is the longest side, divides the triangle into two triangles, that are similar. To each other and similar to the original triangle. Okay, so as you saw previously, I drew a line inside this right angle triangle, and what this statement is saying is that if I draw that line, then the resulting triangles, two triangles which result from drawing that line, these two, are actually similar to each other and similar to the big triangle, so the main triangle. So we're actually going to prove that, and so let's start. So required to prove that triangle ABC is similar. So triangle ABC is similar to triangle DBA, which is this one over here, and all of that is also similar to triangle DAC, which is basically this one over here, DAC. So that is what we want to prove here, right? So let's go ahead and prove that. So to start with, we're going to start by looking at triangles. So in triangle ABC and triangle DBA, let's look at these two first. So ABC is a big one and DBA is the green one, which I highlighted by green. And so if you look at those two, you will notice that angle A1, right? So this is angle A actually. So let me erase that. Angle A, which is from the big triangle ABC, is equals to angle D1, which is in DBA, and both of them are equals to 90 degrees. Okay, that is out of the way. That is just given to us. It's present in the diagram, so it's basically given. And also angle B is equals to angle B because it's a common angle. If you look at this, it occurs in both DBA as well as ABC. So this is a common angle, right? And finally, we can conclude that the last angle, so the last angles which occur in each of these. So for ABC, it's angle C, which is left out of what we've been talking about previously. So it's angle C, and for DBA is basically angle A1, which we haven't talked about, which is the angle over here. So I haven't talked about that angle over there. Now, if the other two angles are equal, this means that the last angle of each of the triangles is equal, or the final two angles are equal. That is what that basically means. And the reason for that is third angle of triangle, because all of these have to add up to 180. So if these two add up to a certain number, then the last one is the only number which is basically left for you to get to 180. So your reason will be third angle of a triangle. And therefore, we can conclude that triangle ABC is similar to triangle DBA. And the reason for that is angle, angle, angle. Now that we've concluded that, we have the first part of the question covered, or the first part of the proof, which is this part, ABC similar to DBA. So that is out of the way. We've actually done that, or we've actually proved that. Now we can come up and, so let's just use this part so we can actually see the diagram as we work along. I should have started here, doesn't matter. As long as you've got to understand that first part. Now this is the second part, and we're now looking at ABC, triangle ABC and triangle DAC, right? So ABC is the big one and DAC is the yellow one, which I just drew yellow lines across. And we can say, or we can see that so basically angle A, which is from the big one, is equals to, which is from ABC, is equals to D2, which is from DAC. And both of those are equals to 90 degrees, and it's actually given to us. So given. And we have angle C equals to angle C. It's a common angle. It's common to both. It's inside DAC and it's also inside ABC. And therefore we can say common angle. And just as we previously did, you can just say B is therefore equals to A2, which is the last angle in DAC. And the reason would be third angle of triangle. And therefore we can conclude that ABC is similar to triangle DAC, and the reason for that would be angle, angle, angle. And so we finally proved that DBA is similar to ABC and DAC is similar to ABC. And if DAC is similar to ABC, it means that it's also similar to those that are similar to ABC, and one of those is DBA. So finally, we can conclude that after writing those two proofs, those two parts, we can therefore say that ABC, triangle ABC, is similar to triangle DBA, which is similar to triangle DAC. Now that we've proven that these are actually similar, or we've actually proven this statement that says if you draw a line from the right angle to the hypotenuse, you have two triangles which are similar to each other and similar to the original triangle, we can actually have proportion out of that, because as you know, similarity is associated with proportion. And therefore, what follows from that is that, so we have corollaries, if you can say it right, corollaries, it's quite tricky to say, corollaries. So the first would be from that triangle ABC is similar to triangle DBA, and from that you're basically going to get AB divided by DB is equals to BC divided by BA. And now if you decide to just multiply through, you're actually going to get AB squared is equals to BC plus BD. And if we go down to actually look at something like ABC similar to triangle DAC, from that you're going to get, let's see what you're going to get. Let's go down. From that you're basically going to get BC divided by AC is equals to AC divided by DC. And if you cross multiply again, you're going to get AC squared is equals to BC multiplied by DC. And finally, if you look at DBA similar to triangle DAC, you'll find that DB divided by DA is equals to DA divided by DC. And if you cross multiply again, you should get DA squared equals to DB multiplied by DC. And we're actually going to use these, so the final steps over here after computing our corollary. It's quite hard to say, so forgive me for that. After looking at our corollaries, this is very funny. Okay, I hope you get my point. I'm only joking. So after looking at your relationship which you have between the proportions, so from the proportions you can actually make these three conclusions once more. And all of this is actually going to help us to prove the theorem of Pythagoras. So that's what we basically want to do now. So up here, after looking at our corollaries, so up here, after looking at our corollaries, we can basically say that we have, or we want to prove the theorem of Pythagoras. So proving the theorem of Pythagoras. All right, so that is what we want to do now. And the statement of this theorem it basically says that, so if you look at the original diagram which we drew, I'm just going to do a rough sketch of it right here. It looks something like this. A, B, C, right? Looks something like that. And the statement says BC squared, this is the Pythagoras theorem. It says BC squared is equal to AC squared plus AB squared. Right? And we basically want to prove using these corollaries, and you're basically going to take the statements in red. Right? So if you look at AC squared, where is AC squared? So AC squared is over here, and we found that AC squared is equals to BC multiplied by DC, right? So AC squared is equals to, this is from our corollaries, and we found that AC squared is equals to BC multiplied by DC. And we found that our AB squared is equals to BC multiplied by BD. So ultimately, AC squared plus AB squared is equals to, we have BC multiplied by DC plus BC multiplied by BD. And from that, we can basically see that we have a common factor on this side, and we can say that, take that common factor out, and we're going to multiply that by DC So that's basically what's going to happen in that bracket over on that side. So we're actually going to have this in our bracket, and on this side is basically just that. And what can we do, or where can we go from this point? If you remember, we actually had a line over here, and at this point we actually call this point D. So now in the brackets we have DC plus BD. So we have DC, which is the same as CD. We have that, which is DC plus BD, which is ultimately equals to, so BC is equals to the sum of BD plus DC. And that is what we have in the bracket over here. So this is the same as what we have there. And we have established that the sum of that is equal to BC, which means this bracket is the same as just having BC, which means indeed this AC squared plus AB squared is equals to BC multiplied by BC, which says BC squared is equals to AC squared plus AB squared. And we have ultimately proven that this Pythagoras theorem is actually correct and it works. So that was basically all that I have in this video. We've covered quite a few things and it was quite interesting to teach, I must say. And if anything isn't clear, please leave a comment. And if you haven't subscribed, please subscribe. If you like this video, just go ahead and give it a thumbs up, and I will see you in the next video.